I start recording. Last week we have already defined those, but we haven't further discussed how could we calculate those. Now, for rise time, assume that it's a step response, step value 1. For rise time, how could you obtain the rise time? How could you obtain the rise time? If you write output CT equal 1, I obtain the rise time. Tamam. So function is this. This is the function. This is the function rising. Now reaching here, then I put 1, then I'm going to find the time here. So I have to write the equation first. What was the equation, by the way? Equation was yt, sorry, ct kullanıyorduk. Bir dakika. Kafanızı karıştırmayayım. Ben genelde yt kullanırım ama kitabınız ct yazdığı için ct ct is equal to, which is equal to 1, which is equal to equation, I reproduce it, 1 minus e to power minus zeta omega n, zeta omega n ne yazayım buraya? What am I going to write? It was t. But for this case, it is tr. Okay. Times parantezi buraya açıyorum. Cosine omega dtr, omega dtr plus those equations are already in your notes. Last week I wrote those equations to you. 1 minus, you don't have to memorize, by the way, equations. You just only to understand what does it mean. Sine omega d tr. What kind of function is this? So it's, what kind of function is this? It's a function. That means this exponential term is the envelope, and that one is the sinusoidal waveform or cosine function. It depends how could you derive those. If you follow that manner, you are going to obtain that. So you are going to write, how could you achieve that 1 is equal to 0? If you look at my cursor, are you following me? What I'm doing now, I'm trying to obtain TR. At TR, it is a function is equal to 1. So if you take 1 equal, that means this part of the equation that part of the equation should be equal to 0. So if you write that equation 0, then you obtain TR, which is equal to, I clean this part, it's already recorded anyway. So it is TR is equal to pi minus beta over omega d. So we have already derived TR. What about TP? What are we going to do? How could I obtain TP? For TP, do you have any idea who is going to give me a hint? I know CT function. I know the analytical equation of this one. How could you tell me to obtain this point? Of course, that means TP. How could I obtain that one? I expect a proposal from you. I know the function of the CT, so what am I going to do? I give you a hint. If you have an analytical equation, how could you find the peak of it? In order to find the peak, what you are going to do is going to get the derivative of this one and make it equal 0. I'm surprised that nobody has answered that question. So if you write dCt over dt at TP for TP is equal to 0. So you obtain TP. I'm going to clean this part again, and TP is equal to pi over omega d. Of course, I'm not deriving all those equations. Pi over omega d. Then the next question, what is m? How could you find MP? All right, you help me to obtain MP, the maximum overshoot. So we are now looking for this value. How could I find this? If I put, for you have already got one CT equation. CT is known. If you put T equal TP, you obtain MT. Sorry, not MT. You obtain, are you following me? It doesn't look, you obtain the function of C output at TP. You obtain CTP. CTP means that point, maximum point over there. So this point, as long as you obtain this point, you can obtain MT, the maximum overshoot, by putting T equal TP and -1. If you, so we are looking for the distance between overshoot, the distance between 1 and that point. So you are going to solve it. Okay. So if you, in order to obtain that one, what you are going to do, TP, sorry, MP is equal, employ that one and obtain, I wrote here, MP is equal to E2 minus sigma over omega d times pi, which is equal to E2 minus, same thing, of course, we know the relationship between sigma and omega d, minus zeta over 1 zeta square times pi. E2 power minus zeta over square root 2, 1 minus zeta square times pi. Okay, so that is the equation for MP. The last thing we are going to find, the last thing is going to be to obtain settling time. You remember that settling time in definition is the one that, if you look at to me, your step response is beginning inside to 2% band or 5% band. So your waveform is not now leaving that one. You can see that those limits you can see from this figure. So how could you do that? You employ the, we already derived the function of this waveform. So we are going to write that one and equal to 0.05. As long as you put 0.05, you obtain the settling time Buraya yazabilirim herhalde ya. Başka bir renkle yazayım. Şey yapsın size. Yardım etsin. TS is equal to 4 over sigma for 2%, which is equal to 3 over sigma, which is equal for 5% criterion. So bundan pek mutlu olmadım ben çocuklar. Bir dakika. Şurayı sileyim işte ise. For 5% criterion, TS is equal to 3 over sigma. So sigma, the real part of the poles, are decisive to obtain the settling time. We have a problem here now. We are going to solve the problem. Okay? If you are happy about those, so I'm going to continue to solve the problem here. Just go to the clean pages. Yeah. Problem is this. I read the problem. Consider the system where a system zeta is already given. Okay, it's easy. Zeta is equal kaçtı? 0.5 hatırlıyorum. 0.6 omega n is equal to 5 radian per second. Let us obtain the rise time TR. Ondan sonra peak time TP. Ondan sonra omega n, rise time, peak time, maximum overshoot MP, maximum overshoot, and settling time TS. Settling time için şey vermemiş. Şimdi what are we going to do? We know that solution omega TR is equal to pi over beta, you remember that we have already derived those equations. Pi over beta over omega d. What's omega d then? What's beta then? Omega d is equal to omega n times one minus zeta square, which is equal to omega n is 5 square root 2 1 minus 0.36 değil mi? 0.06'nın kare, eyvah. Kaleme bir dokundum bir şey yaptı ya, Allah kahretsin. Şimdi sileceğiz onu. Ne yapıyor, ben anlamıyorum. Bir daha yazdı aynısını. Demek orada bir komut var kalemde, ben iyi bilmiyorum. Pat diye aynısını bir daha yazdı ya. Kalemin şeylerine hiç dokunmamak lazım. Evet. Şu zeta'yı bir düzelteyim. Zeta square. Zeta 0.6 olduğuna göre 0.36. O da eşittir. Yapmış hesabı kitap. Ben oradan bakıp söyleyeyim size. 4. Sigma kaç burada? Sigma which is equal to zeta omega n. O da eşittir. Zeta 5'ti. Pardon. Zeta 0.6. Zeta is 0.6. Omega n is 5. 3. 0.6 çarpı 5 eşittir 3. Şimdi beta'yı bulmamız lazım yalnız bu denklem için, şu denklem için. Beta is equal to, you remember that that one is sigma, that one is omega d, this is j-axis, this is real axis, and that is the point location, and beta is the angle here. If you connect pole to 0, origin, beta is this angle. This is beta. So beta is equal to tangent arctanjant diğer bir şeyle omega d over sigma, which is equal to four over 3, which is equal to 0.93. So we already obtained beta. So TR then, şu beta'yı burada da kırmızı yapayım. Beta. Evet. So buradan TR is equal to pi minus 0.93, sorry, 0.93 over omega d, which is 4, divided by 4, which is equal to 0.55 second. So half of the second, it reaches to 1. What about peak time? Peak time. Peak time equation was T peak is equal to pi over omega d, which is equal to ben bunu kullanırım. 1.6'ya kadar giderim genelde. Kitabınız gitmemiş. 4 divided by 4 which is equal to point second. So peak time, of course, rise time is the early one, reach one step value, but there is of course overshoot. Then overshoot occurs in 0.78 second later of the beginning. MP here MP is equal to E2 minus sigma over omega d times pi, which is equal to you help me, I couldn't write, minus, you can see that, follow my cursor please, you can see that sigma is here, so I'm going to put sigma 3 and omega d is 4, so minus 3 over 4 minus 3 over 4 times pi, which is equal to 0.095. So that means overshoot is 9.5%. Okay, it's 9.5%. We already obtained. It's a nice, by the way. Below 10% is very nice overshoot. So if we continue same manner, settling time is equal to 4 over sigma, which is equal to 4 over 3 is equal 199, sorry, 133. However, it might have been 3 over sigma, which is 3 over 3, which is equal to 1 second. Now I have a question. Which one is 2%? Which one is 5%? I draw the response here. Step response. And what's happening here? The response is this. So this one, T peak, this one, T rise, which is 1 second. This one is more than one. Bir dakika. Kaç bulmuştuk T rise'a? 0.55. T rise 0.55. T peak 0.78 second. This is of course time. And this is response. CT. Response. Neyin responsı? Step response. S olacak, C değil. Evet. Şimdi gelelim buraya. That one is longer time. That one is shorter time. That means this one is, of course, it's a shorter time is a 5% criterion. 5% criterion. That one is 2% criterion. Which one you prefer? Okay. So we have solved the problem, and now we know how to calculate. We know the analytical equation of the system. So we can, if you know the system, knowing the system means that you are knowing zeta, you are knowing, and also omega n and other parameters. Last week I have already shown that for mechanical system or electrical system there are equivalent laws that transfer function TF omega n square over z square plus 2z, sorry, s square plus 2z omega n s plus omega n square is represented by either electrical network or mechanical network We have already proved that one. So I strongly advise you to make the link between that equation here, this equation, sorry, this equation here, the link with the real physical systems, either mechanical. That is very important for me. And as long as you obtain the link between that analytical equation, of course, electrical people are familiar with this one, since this is a typical response, and you can obtain the resonant, for example, frequency from this one. If it is a LC network, you can obtain LRC network, you can obtain those. But for mechanical system as well, you can obtain that. Okay, so that's very important for me to understand. And we already calculate rise time, settling time, and everything. Okay, so I come back to original slide material, which I believe this last week we haven't emphasized that one yet. That's why I completed this. That is the location of the pole. For, of course, if it has real and imaginary parts, we know that it might have been real parts as well. And this is typical step response we have already driven, and we have already calculated the settling time, rise time, and everything. That is a continuation of it. Yeah, that's right. This is the problem we have solved. And that one is, I emphasized the mechanical equivalent of the system last week. You can see that for transfer function here, for example, if I ask you what's omega n, you can tell me. Can you? What is omega n here? Anket açıyorum. Omega n is equal to P over J. You are going to answer evet or hayır. Yes or no. Okay. No response means that yanıt yok. That means you are not in the classroom. So either you are going to tell me yes or no. Right? Why did you write here? Did you answer that anket question, the questionnaire? Come on, go on. Still 8 students couldn't be able to answer. Probably they're not in the classroom then. Hadi. Hurry up. Hamido, where are you, Hamido? Hilal Bassam, Hüseyin Mahir, Mahmut Ramadan, Ozan Akkoç. Ozan, you were in the classroom in the beginning. Have you left? Yunus Emre, Yusuf Selim, no answer. What's going on? You are not in the classroom then. Dersi dinlemiyorsunuz. Demek ki derste değilsiniz. Yani açtınız dersi sonra gittiniz. Sonra nasıl okurum diye. Tamam Ozan, teşekkür ederim. İyi yaptın, yazdın. Hakikaten üzülüyordum, biliyor musun? Yani seni iyi tanırım, biliyorsun. Peki, teşekkür ederim yazdığın için. Kusura bakma. Günahını aldım. Başka Hamido, are you there? Hilal, Hüseyin, Hamido.
Yes,
Good,
I'm
you
here,
are
sir.
there.
I'm here. Yeah, I'm
Okay,
here.
all right.
Yeah.
All right.
Yeah.
Yusuf and Hilal.
Uh-huh.
Okay, so I'm now closing it. I'm asking, who was the still 4 person? Hussein is disconnected, so it's all right for Hussein Mahir. Who was the person who put no first, then change it? Open your microphone and tell me, why did you change this? Okay, so I'm closing it. So you have already said, yes, it is correct. Okay. Five-person couldn't be able to answer, but Ozan is there. Just he couldn't connect. And probably Yusuf Selim is already over there as well. Hüseyin Mahir, was it you who changed the Hüseyin Mahir, was it you who changed the decision from no to yes?
I did so. It
You
was
did.
it was a
Why
yeah.
did
It was.
why did you change? Why did you change, Hüseyin?
No. It's not me. It's the internet. It's the
Okay.
internet. Yeah.
Okay, all right.
Yeah. Yeah.
All right. Now I'm going to answer. I'm very disappointed. I'm very disappointed. So if you look at that one, here is K over G. K over G here is omega n square. So omega n square over S square plus 2 zeta omega n S plus omega n square. So that one here is omega n square. So omega n is actually omega n k over j. I'm very disappointed. Okay, nobody answered correctly. There is no one who answered correctly. One person put first no, then change it to yes. Okay. These are we have discussed before. We have already last week. We have already studied that one, and we have derived the equations. Those equations we solved that one. We obtained zeta and the other parameters for inner loop. That's the unit impulse response of the system. That is the unit impulse response of the second order system with parameters of zeta. You can see that we have already. Of course, if you write the equations, you can obtain that one. We have last week, we have also discussed that one. You remember that. The poles like this, follow my cursor. That pole here is far away from omega, so it's far away from origin. So the length here is higher. However, that one is even isn't longer. But as long as the real part of this one is smaller, close to the origin, so the decaying speed attenuation is less than this one. These are far away from origin. The transient response is very high. So these effect of these poles are diminishing. I repeat, the effect of those poles are diminishing faster than those poles. That's why these poles are called dominant poles. So if we are going to neglect between those, you are going to neglect the faraway ones. You understand? But also we emphasize that as long as you go up, that means omega is rising, then your oscillation frequency gets up. As long as you get down, your omega, the oscillation frequency gets down, down, down, and then when you touch here, it becomes zero. There is no oscillation at real axis. It's obvious. And also the transient response of this one, this pole, is much faster than this one. However, there is another story. If your poles are located on the G omega axis, that means you have continuous sustainable oscillation. The frequency of the top one is higher than the frequency of the bottom one. However, if go further to the right hand side of this one, your system becomes unstable. Today we are going to discuss that one as well. If you have more zeros and more zeros and more poles, that means your numerator has got a lot of roots and your denominator, which is a characteristic equation, has got a lot of roots. So that is higher. These systems are called higher order systems. Okay. For higher order systems, we use generally MATLAB to solve those. These are the zeros. You can see that m times 0 we have, and the n times pole we have. Poles are higher than zeros. Don't forget that. the characteristic equation order is always, characteristic equation means the denominator, order is always higher than the numerator equation, or giving us the zeros. Okay, and that one we have already discussed, and the answer of this one, the dominant poles are -1 and +1. -5 and plus J5 is far away from origin, and their effect diminishes faster than the dominant poles. Okay, so that's the end of this lecture. I'm going to this topic is continuing. So the next lecture I'm going to open it up, but before that we'd better take a break. It is already 10, 11:15. All right. Sorry, 10. 16 yazıyorum. Bir dakika daha geçti çünkü. 10 dakika ara veriyorum. Okay, see you then. Take a break. Hello all. I'm just starting a new chapter, transfer function and state space calculations. And I specially designed these slides in order to improve your knowledge about the MATLAB as well. Of course, you are going to get you are already having MATLAB equations. Now, state space is a different approach. It's a time domain equations. I'm not going to emphasize on state space, by the way. During that undergraduate education, we do not emphasize, we do not base upon the control theory based upon the state space, but you have to get some idea about it. We define state equations, state variables and state equations. And the state of the system is set of variables such that the knowledge of these variables and the input functions will with the equation describing the dynamics. So the dynamics of the system is already defined, by the way. It's a good method, but pedagogically, when you complete your controlled concept, it is easy to understand later. But when you graduate it, probably you are going to work on state space method as well. Therefore, you have to familiar with. Now, first, the state variables we define. System is something like this. These are that X here is a state variable, a linear continuous time control system, time domain. And in state space, the equations are represented like this. X dot, you can see that only first derivation is involving, but it's a time function. You can see that it's a time function. So A times X, this one is a matrix, by the way, A. B is a matrix. A is a state matrix. B is a input matrix. X is a state value. U is the input, by the way, input of the system. And the output, that is the equation. X dot is equal A times X, B times U. These values, the matrix values, are represented like this. Y is the output is equal C times, C is the output matrix, times xt, again the function of state variable, and D times that direct transmission matrix is not commonly faced with, but it's also proportional with U output. So if you look at the equation here, we have, bakayım büyük yapmıştım bir tane. Ha, yok, bununla idare edeceğiz. You can see that. Can you see this one, this point? That is X. X times A plus U times B is equal to X dot. Burası tamam mı? I repeat. That is X. So X times A plus U times B is equal to X dot. X dot integrated, you obtain X. X is multiplied with C, plus you have D, effect of D is coming here, you obtain the output. This is the output. So this is the block diagram representation of those state equations. This is state equation, the other one is output equation. But it's all defined in state space. In Turkish, durum denklemleri çocuklar. Bunlar durum denklemleridir. State space equations. For example, if you have a system like this, how could you solve that kind of system? Be careful. It's not a vehicle problem. It's something hypothetical, since that part is reference, and also this part is reference, so there is no motion. So the action is defined with respect to those reference values. And also we assume that we have a force affected. I criticized Professor Ogata that if you use U for position, don't use it for force. Just write it force, F. So this is a force, by the way. Okay. And this is a mass. You remember the state equations. We'd better write first we remember the S domain equations in time domain. We can 5 punto çok kalın. Şuraya sığdırırım. M times y is the position, double dot, plus başka ne var orada? B times y dot datları bir kuvvetli yapmışım. Gene kuvvetli yapayım. Plus k times y is equal ut. This is the equation actually. U is the external force, and this displacement is y, and also it's an equilibrium point, so there is no initial stored energy in your, particularly there is a spring here. Obtain the state space model. So state space model, this is our model, time domain. And if we come back to the S domain, of course, we are going to obtain M S square plus BS plus K times Y is equal U. So transfer function here is equal to 1 over S square plus B over MS plus K over M. Bir yanlış var burada. Kim bulacak? Who is going to find the error? I divided by M, so that one is also should be 1 over M here. Sorry. Tabii transfer function. Output nedir? Output YS is equal to US times TF. So that is what we have done so far. Let's look at the state equations. Now that is the equation I have already written. Now what we are, it's a second order equation, but state space equations are the first order. Then what you define, this is the definition. X1 is equal y. So we define y is equal x1 in time function. And x2 is y dot. These are definitions. As long as you define like this, x is a state variable, state variable. So x1 dot, which is equal to y1 dot. So x1 dot is equal to x2. So then here, this term, we get rid of the second derivation. It's actually the first derivative of this one. And 1 over m minus ky minus by dot plus 1 over mu is the x2 here. So if you write here, so if you keep it y double dot alone, bunu yazı vereyim şuraya. In our case, that's the one here. So what you do actually here, you can see that one is here, this one is there, and the last one is over there. So it's that easy to write those equations. Well, we have two equations now. That one is you remember that one is the first equation, this one, the first equation, and this one is the second equation. So I go back. This one is the first equation, that one, and that one is the output equation is equal to this. In order to make in matrix form, you can easily write x1, x2 your state variables, 0 times x2, sorry, 0 times x1 plus 1 times x2 is equal to x1. Bakalım öyle mi? Yes, x1 is equal y. So sorry, x1 dot is equal to x2. Öyle mi? x1 dot is equal to x2. Öyle. Gelelim buraya. x2 dot times k minus k over m times x1 plus minus b over m times x2 plus 1 over m times u. That's exactly this equation. That's exactly this equation. x2 is equal to the y here, of course, y here is x1. Bunu bir daha yazayım şurada. Daha kolay olacak sizin için. Başka renkle yazacağım. So I wrote this equation again. So x2 dot is equal minus k over m x1 minus b over m x2. So if you look at here, what we are actually forming, x1 dot x2 dot equal a times x1 x2 plus u, sorry about that, bir dakika ya, bunun matrix formu vardı. Evet. Buraya sığacak mı bilmiyorum. Biraz geniş gitmişim. Bir dakika çocuklar. Heh. Allah Allah. Yok, bir aksilik oldu çocuklar. Git silmiyor onu. O zaman oraya ben sığdıracağım bunu. Okey. times U. Burada yukarıda aynısı yazılı zaten. That's the one here. So you can see that A matrix is that one, this one here, and the B matrix is this one, and C matrix is 100, and the D matrix is equal to 0. So this is the solution of this system. So I come back to system. So this A is a state matrix, X is a state variable, U is the input, by the way, B is the input matrix, and output is the C is the output matrix. D, generally we don't have D here, okay? Direct transmission matrix. This is what state space approach is all about. I omit those. Correlation between transfer function and state space. So that is there some equations are involving here. I don't know whether you could follow me, but I'm going to just give you those equations to you. Now this is our transfer function, okay? GS, transfer function. However, state variables x dot is equal to ax plus x dot görünüyor mu bilmiyorum. Ben göremiyorum ama biliyorum x dot olduğunu orada. Evet, görünüyor. X dot ax plus bu, c is cx plus du, and if you write those equations in that manner, s times initial, if you have an initial value, the x this one is equal s times xs minus xo. That one here is axs plus bus. As we come back to time domain to s domain, and ys is equal, we come back to s domain from time domain. State variables and state equations, state space method is in time domain. Don't forget that. Anyway, so if you come back here, cxs times dus, continue in that manner. I repeat those equations. X1s is equal to, so if you convert this one here, you can see that s, that I here is unit matrix, minus a to minus 1 is in denominator. So if I take that part to denominator, I obtain ys is equal c times si minus a power to minus 1. That means 1 over ci minus a times b plus d. So this is the transfer function of the system. So we derived ys here. So if you divide it by us, then you are going to obtain the transfer function here. This is the equation of that one we have already derived. So if you solve it, I'm not going to solve it that one, but if you solve it, you are going to obtain S domain equivalent of this one, which is we already have got that one, 1 over ms squared plus bs plus k. Okay, you can obtain that one. So there is a relationship between state space equations and transfer function equations. Transfer function equations are in S domain, state space equations and in matrix form and in time domain. Tamam mı? Bu kadar sizin için yeterli. Şimdi ne yapacağız? Çocuklar, ne yapacağız? We are going to use the MATLAB for this one. Do you know, have you learned how to write step function, for example, in MATLAB? You just write step num then. MATLAB representations of the, I omit those first. Yeah, the MATLAB representation of the system. For example, that one, how do you write the MATLAB equivalent of it? And how do you get the step response of it? So I'm going to give some time to you. So I'm going to devote, although I expect Seyit, my assistant, is going to give you, Seyit Hoca is going to give you some detail about this one. However, in order to write that one, I have to open up a clean window for us. Bakayım başka var mı burada ya? No. For example, CS over RS, output divided by, is a transfer function. Assume that you are going to have 2s plus 25, s square plus 4s plus 25. What you are going to write here, then num, in MATLAB, you are going to write num numerator equal, bu eşiti çok unuturum ben ilk başlarda. Şimdi bakın bunun order'ı 2 var burada. Bunun order'ı 2. Second, the first order. So you don't have to write 0 here. Just put 2, bir boşluk, space, then 25. Then 25. Buraya bir noktalı virgül koymayı unutun. Ondan sonra arayın durun. Tamam mı? Unutmayın noktalı virgül koymayı. Altında kürsör yeniden yanıp sönmeye başlar. You are going to write then denominator which is equal to 1 boşluk bracket empty space 4 and 25. Then step num then dediğiniz zaman bir tane step num then'li şey arıyorum da size örnek. Neyse şuraya yazayım. Dediğinizde bir tik atarsanız size şu fonksiyonu neyse o fonksiyon onu verir. Neyse o fonksiyon. Draw the curve. I don't know. Step value şu da step value olsun. It'll draw this is time, this is function step. So this is the one you are going to do that first. The for S domain, that's the case. However, for state space method, you are going to write state step A, B, C, D is going to give you plot the curve. you might define the system transfer function num and system, then step system, then you are going to obtain that one. So if you have any further, so you are going to capable to draw those curves, okay, in MATLAB. One example. For GS, (25) over S square plus 4S plus 25. Bunun için yapacağın şey num eşittir equal 0 0 25 then buraya noktalı virgülü koymayı unutma. Then you are going to write then equal 1 4 25 then step num then you are going to get enter diyeceksiniz buraya, tamam mı? Enter'ı şöyle göstereyim. Enter. It's going to automatically draw the curve. I don't know how many of you have got Ogata's book. Ogata's book has got a lot of examples, drawing MATLAB examples plus solved problems. It's a beautiful book in that sense. That's why I follow the book in order to help you to define those. You can find rise time and also the settling time and things like this. You can do that. Well, you can practice it, this one. I'm not going to spend more time on this, drawing those curves, but for MATLAB application, if bir example vereyim. Bir example vereyim şeyle ilgili. For state space, hazır kırmızıya alıştırdık sizi. Kırmızıyla vereceğim. I'm going to give it to red. State space x1 dot x2 dot is equal to 0, 1, minus 1, minus 1 times x1, x2. Plus 0, 1 times u. Okay. And y, the output, is equal to 1, 0 times x1, x2 plus 0 times u. These are state equations. You remember that. A matrix is this one. B matrix is that one, which is a vector. And this one is our output matrix. So that one here, if you write the MATLAB equation now, A is equal to 0 space 1 comma dot minus 1 minus 1 space minus 1. Oh no, bir mistake'im var. I have a mistake. I'm going to clean now. I did. Okay. B is equal zero noktalı virgül 1 C is equal one space 0 D is equal to 0. Now either you are going to write step A, B, C, D, or if you want impulse, for impulse, you are going to write impulse A, B, C, D. Then of course you are going to write grid and title and things like this. So it's going to, this one is going to draw step response of this one, and if it is impulse, so it's going to be A, B, C, D it's the same statement for impulse 2. For our case, this is state space approach. For our case, for example, for impulse, onu maviyle şey yapalım. CS over RS is equal to 1 over S square plus 0.2S plus 1. So if you write, you help me to write num equal, ne koyayım buraya? The order is here 1. Then kafamızda bir den oluşturalım. Without completing the num, you cannot write the den. But on the board I can do that. Den kaç bu? 1 boşluk bracket empty space 0.2 and 1. Here then it's going to be 0 space 0 then 1. Don't forget to put comma, dot comma. Then you write then equal this one. So if you write here impulse instead of step, impulse, gene ne oluyor? Impulse numden grid and title. If you want to write the title for title, you are going to give comma here and write whatever you prefer to write. Ne oluyor ben anlamadım. What's going on? Neyse bunu hemen parantezi kapatayım bitsin bu iş. Nedense bir küçülüyor bu. Şöyle kapattım. Tamam mı? Şöyle tırnak için alıyorsunuz. And you write whatever you prefer to write. Okay. So let's go back to our course material now. I'm just going to give you a brief summary what we have done so far. Just don't lose what's going on here. Lecture 6. Now we started with, after the break, we have started to define the state space method. The basics of the, listen carefully, the basics of the state space method is such that we write the equations in time domain. This is the first point you should not forget. The second one, we get rid of the second derivation. There's no second derivation here. So what we defined as the x1 and x2, then x1 dot and x2 dot. That's all we define. And if you write the equations like this one, x1 dot, for example, for it might be a single value or single input or single state variable, then A is a state matrix, B is the input matrix, and that is the equivalent representation. And you need two equations. One of them is state equation, the other one is output equation. In order to solve those, there is a relevant the relationship between S-domain solutions and the matrix version state space solutions. However, for state space, I don't want to involve too many hand calculations. Instead, if you write those matrices, then you are going to draw your curves, step response, and things like this in MATLAB. Okay, as long as you derive like this, then you are going to give those equations in MATLAB and say that step A, B, C, D, and then you are going to draw the curve or impulse A, B, C, D. So matrix, and that is the typical electrical equation. You can also write the state space equations of this one as well. The relationship between state space and Laplace S-domain is already established. This one is the solution for the relationship, and at the end it's shown that I'm not going to do that. For those who are interested in follow the equations, you are going to obtain at the end, by the way, you are going to obtain that from starting state space and then coming to the S-domain transfer function, you obtain the same equation. Okay, I'm not going to involving those matrix equations. And transient response analysis with MATLAB, you are going to write step num den or step num den t, step ABCD. For impulse num den, impulse ABCD. These are the examples here. If you write down those equations in state space and give the solutions, you are going to obtain four outputs. This is a multiple input, multiple output system. You are not going to be responsible for that. However, these are for MATLAB state space program is easily give you the responses of each input output. That is the one. I think I have done this for you. The unit step response curve. Just write the system and num den. It's all right. And that is two-dimensional plot of unit step response curves. That is the equation, and you change the zeta, you can draw the curves as well. For unit ramp input, so what you are going to do, if you do not write it, you can come back to step unit ramp response curve. This is the action between transferring from transfer function approach to state space or in other opposition direction. For example, if you write ABCD TF transfer to SS num den, then you are going to get the conversion. For example, if you have num then you can convert, you can obtain A, B, C, D, the state space. So you can convert those. Now I'm going to give you a very short break since I'm going to start a new topic. It says stability. Okay. So a very short break we are going to have. Very short break means that it's time now 14, 15, 11:25. 11:25. 11:25. We are going to start stability. Okay. Hello again. You remember that when the transfer function roots are located in the right-hand side of the j omega axis, we define that system is not stable. Of course, that system here is a stable one, okay? And this one is unstable. Although while it's rotating, it remains like that, but this one is unstable. There is of course in every mechanical system there are equations governing the representing the system. That system is probably might be defined as static system, that one. However, when the vehicles moving or the side wind coming, then of course system becomes dynamics. And if you look at to me, so it vibrates. So you all know we have 3 bridges in Bosphorus. So you all know that there is a kind of motion occurs here. So there are governing equations. If those governing equations frequency reach to the resonant frequency of the system, mechanical system, then the additional forces occurs and that might cause damage. But that what I would like to explain here, that you remember if the roots are located here, for example, one of them is there, the other one is there, but somehow if they move to this part, then your system become unstable. So this is unstable part of the system. So the roots should not be located here. Okay. We all said that closed loop poles lie in the left-hand S-plane. The Routh-Hurwitz criterion is easy method to find out whether the system is stable or not. It is not, sorry, it is known that the following polynomial, which has characteristic equation of transfer function, denominator, all roots should be in the left-hand side of the S-plane. We all know we already know that. So roots should be in the left-hand side of the S-plane. Coefficients are real quantities. How could we evaluate that one? This is stable. This is the roots are located in the imaginary axis. It's although it's a sinusoidal output or a continuous output, but this is unstable. If the roots are located, one root is in the left-hand side. You can follow my cursor, please. One root is in the left-hand side without any oscillation, since roots are located in the real axis, and another root is in the origin, then it's a continuous signal, and that one is unstable, right-hand side. Now, I'm not going to give you detailed mathematical background of the Routh-Hurwitz criterion. However, if you have, follow me carefully, if you have a characteristic equation is equal to this, an times s to power n, then s to power n minus 1, and then a1s plus ao equals 0. So you are going to put those values in a vertical line. The maximum power is s power to n, then one down, one down, one down, then until s to 0. The first two, we locate the constant an here and the an minus 2 here. You omit the, so these are the first one and the one omit and the other one, and n minus 2, and this one is n minus 1, then n minus 8. These are the constant, by the way. Tamam, constants. So these are constant values. So when you multiply an minus 1 times an minus 2 minus, so if you multiply with this one, kolayca renkli bir şeyle göstereyim. Evet. Şunu, you multiply this one with that one, minus you multiply with this one with that one, divided by to the original one, divided by the original one. For this one, however, you multiply that one with this one here. Sorry, first that one to multiply with this one here, minus this one to multiply with this one here, and then divided by the original one to this one. Şimdi, we'd better make an example, easy example. These are the tables telling us what are the reason to have stable system. That means if these are the equations are the denominator of your transfer function, means that the characteristic equation, this one is your characteristic equation, and if that relationship is obtained, your system is stable. Forget about that one, since we are going to derive those equations. For example, these are of course stable system, and the R1 and R2, sorry, R1 and R1 prime, the symmetrical of this one, are dominant poles. R2 has got some effect, but you can neglect R3 and R3 prime. Anyway, that's not main topic. So let's solve this one. How could you solve that one? This is your, first of all, this is your system's equation. So the transfer function of this one, TF is equal 1 over S So at the end, when you solve this one, you are going to obtain this transfer function. TF. So what we are going to do now, we are going to write the routes table. I'm going to draw it here. S3 S2 S power 2 S1 S0 S3 here. So if you look at the transfer function, it's 1 and 2. For S2 now it's 1 24. For S1 1 times 2 minus 24 over divided by 1, which is minus 22. So that one is minus 22. If I'm not making any mistake, 1 times 2 minus 24 divided by 1, that's right, minus 22. For this one, however, 1 times 0, 1 times, so this one is 0. For that one, however, 22 times 24 minus 0 divided by 22, so this one is plus 22. I repeat, minus 22 times 24 divided by minus 22, so two minuses cancel each other, so obtain plus. Now we have, so this is the route table. So if any change occurs between the sign of it, then that means one root is in the opposite side, the right hand side of the S-plane. I repeat, probably you may wonder here. So those line, the first line, should not change any direction. This first line you obtain should not change any direction. Any change from plus to minus or minus to plus, any change result that you have that number of poles located in the right hand side. So if we come back to this example, how many poles do we have in the right hand side? One change occurs here, so one pole is located there, and another change here, another pole. Therefore, two poles are in the right hand side of the system. So if I come here, of course, this is that one is the transfer function. Whatever I did, it put here. So 1 minus 22, one change, first sign change. This is the second sign change. So there are two poles in the right hand side of the system. So, by the way, I deliberately put it from the other book for your improvement in MATLAB. You see, using the pole function to compute the closed loop control system poles of the system. Geri dönelim example'a. Numerator is 1. But denominator'da we have 4, 1, 1, 2, 23. Bakalım ne yazmışız oraya. Yeah, that's right. Numerator, num g, function g, is equal to 1. So bir noktalı virgül. Denominator g is 1, 1, 2, 23. System g, this is a new definition for you. Transfer function num g den g. Şimdi mesela you may write if you want, you can see step numden. If you write step numden, you can draw the step response. Or if you write impulse numden, then you can get impulse function. However, here we are now looking for the poles. So we first write the num, then write the denominator, then we define the system, which is transfer function numden, then system feedback system 1. So that means system is solved. System G is artificial. System is solved with feedback. So that means 24 is going to involve, you remember. Then whatever you write here, pole system, bakın bu çok önemli. So whatever, for example, if I give you s to power 5, s to power 4, you can easily obtain the poles here. When you write pole system, it directly give you -3 plus -2.6 plus 1 -2. So that means roots are located this one is real axis. Beğenmedim. So -3 here. -3. However, this one is -1 plus 2. One pole is located here. The other pole is located there. One pole is located here. So we have 3 poles. This one is 1 here. That one is 2.6. 2.6. The imaginary part. That's -2.6. Another imaginary part. However, the real part is 1. So we have 2 poles. As a result, you don't have to bother anymore for the equation s to power 5, s to power 4. So the higher derivatives involved. Don't worry, you can obtain the poles by using that statement. Evaluate the stability of this system. Zannedersem yaptık. Bakayım ikinci slaytta var mı? Evet var. Bir dakika, yok, aynısı değil. Bunu bir hemen evaluate edelim beraber. ...12'ye 5 kala bırakacağım çocuklar. Follow me carefully. Şey alacak. Seyit Hoca herhalde oradadır. Bakayım orada mı? Daha gelmemiş. Evet. Şimdi bunu çözelim. What's the transfer function of this one? TF is equal k times 1 over 1 plus 1 over that one, which is equal to k over plus k plus 1. Aşağı indiriyorum o zaman. Transfer function is equal to tf is equal to k over s power to 3 plus 2s square plus 4s burada k vardı. Burada k vardı. Plus 1 plus k. Doğru mu yaptım bilmiyorum. Şimdi bunu şuraları silelim. Bunu bir taşıyalım. Doğru mu yaptım bir kontrol edelim çocuklar. K over 1 divided transfer function 1 plus k over transfer function. So if you multiply that one s power 3 2s square 4s plus then of course 1 and also there is a k here. Bir dakika ya 1 yok burada ya. Yanlış yapmışım. Hiç bana bak hiç içinizden biri ya bu ne yapıyor bu hoca falan demiyor musunuz ya? Bak. Şimdi burada aceleye geldi bu iş. Şimdi if you iyice yoruldunuz mu? Ne oldunuz? Çocuklar dağılmayın. Toparlanın. If you multiply for this part so you multiply that one with 1 plus k. Burada k var sadece. 1 değil. Şurada k var. This is k. So it's become plus k. Tamam. Şimdi kontrol edelim bakalım gidelim. Şurayı silelim. Şurayı silelim. Niye 10 punta silemiyorum ben bunu ya? Allah Allah. Silmiyor evet. Neyse işimize bakalım biz. Oraya yazacağım da onun için siliyorum. Evet. Temizlendi. Evet. Şimdi yazıyoruz. Power 3. S square. 1 0. That one here, this one is 1. Then omit the square of it, 4. That one here is 2. And omit that one is k. Wasn't it correct? It is 1, 4, and 2k. Is it clear now? Bu bilgisayarla benim aram bozulacak yakında. Now, 2 times 4 is 8. 8 minus that one here. 8 minus k divided by 2. That one here, however, 0. For this one, 8 minus, by the way, 8 minus k over 2 times k over 8 minus k over 2. So that means this one is k. You are dividing this one. I repeat. 2 times 4 is 8 minus k divided by itself 2. However, for this one, there is no such thing here, is 0. For this one multiply k divided by this one. Therefore, this cancel each other, only k remains. So 8, in order to get the stability, this one one is plus, 2 is plus, that one is questionable, that one is questionable. So that means 8 minus 2 minus k should be higher than 0. That means k should be smaller than 8. For this one, however, for that one, k there is something funny happening in my computer. Google try to help me, but make a lot of problems to me. Anyway, so I continue. K should be higher than 0. So result K should be smaller than 8, but should be higher than 0. That is the result. If you give, so as a controller, now you are approaching to control problem. So this is your gain. You are capable to control the proportionality gain. Assume that. So if you select 9, then your system becomes unstable. But if you select 0.1, no, it's all right. You cannot select a negative point. Okay, so K should be higher than 0, is a positive number, but should belong to K, should belong to 8. Okay, your system becomes stable. There is another example, but I have no time now. Mohammed Said is already in the classroom, so I'm going to leave you. Just before leaving you, I'm going to get attendance list. Don't leave. So Mohammed, Said, you can take the classroom. I talked about state space and transfer function methods, and also give some MATLAB um, statements for drawing step numden and also impulse numden and things like this. So it's all yours.
Thank you hocam.
Hadi bakalım. kolay
Okay
gelsin.
guys, let's have maybe 5-minute break and then be right back here. Ara verdiniz mi hocam?
Ver bir 5 dakika. Ben yani aşağı yukarı yarım saatten fazladır ders yapıyorum. 40 dakikadır falan ders yapıyorum.
Tamamdır
Ver bir
hocam.
5.
Hello everybody. I shared the lab report in here. You can take a look. So today we're gonna do a servomotor modeling and first order electrical systems. So let's take a look our system. We have a MATLAB Sublime model here. We have our parameters, and then we're gonna simulate this transfer function. Let's start. Okay. Okay, guys, let's start to model our function. So first, we have our step function. We choose our step function, and then we have our transfer function and sum. You just write TF in a library. You can just find the transfer function, and we're gonna use a sum product. And then we have a subtraction, just saturation, for limit our current. And then we will use our feedback gain. What else? We're gonna use a scope for observe our output. Guys, do you see the PDF file that I shared with you? Can you see it? Okay, let's start to build our model first. We have step function, we have some product, our transfer function, our saturation for limit the current, where saturation is just you can decide 2 points and just limit your parameter. And then we have gain or gain. Of our scope. Okay, so let's start. First, your step input, your function will go in some product, and we have a gain. So let's just rotate our gain. When you can format, you just set flip block. You can change it. Say connected, but this one will be subtraction. So the second one, you can just double click it and make it the minus, and you convert to the subtraction. So this comes to your transfer function, and then it goes to your saturation, and then you connect it to gain, your second transfer function, and then you go to the scope. And we'll get our gain from the output, of course. So let's take another scope to here. Observe the current in here. Yeah, so in our model, we have parameters that I shared the file in Euler. You can check it later. So our first transfer function, all right, 1 over LA S plus RA. So our your resistive load and your inductive load, the first one will be 1, and your dominator will change. So you're gonna change it to your LA value. It was 0.85 Henry. So the first value is 0.8587 Henry. And then your second value, your resistance, which will be 0.59. Right, you just apply it, okay. And then your second transfer function. Because can you follow everyone here? One student, all right. Two, okay, good. Okay, at least someone following, good. So our the first we decide our first transfer function. We said that our denominator is our inductive load and resistive load, LAS plus RA. So 0.87, 0.59 that we value parameters we decided. And then your saturation, we current the limit, so between the plus and -3 is for limit the current. So you can use this saturation point for limit your parameters. Yeah. Okay, and then you have your gain value, all right, which we're gonna decide it later. And then your second transfer function here. Your second transfer function is 4.7 for the inertia, all right, your load inertia. And then let's decide the first one is 1. 0. Decided to be 4.7. 4.7, all right. And then your second value will be the FM, which is your source impedance, all right. The second value will be your source impedance, which is we decided to be 1.68. All right, you just apply it, all right. And now for your gain, for the gain, we're gonna change the gain, but we'll start with 1, 2, 5, 10, and 100, and we're gonna see the difference between them. So first, I want you guys to find the settling times as a homework. Like next lab, we're gonna discuss about settling times. The settling times is the time required for the response to reach the steady state. You know, we said our system has a steady state, right? Every component has a state. So to required response to reach the steady state and stay within the specific tolerance bands around the final value. So this is our settling time. All right. So we're gonna take a look at graphs too first. And then our gain first will be 1. This one is 1. Right. Our gain, let's start with the 5-second one. All right. And then let's start. Take a look. All right, you see your system. I ask you to find the settling time. All right, so settling time is this. Look, we have our system, right? System response has a peak, and it has a value between the peak, the maximum values. All right, we have a tolerance between 2% or 5% tolerance, and our response value should be between the two tolerance band. All right, so time between the system to reach the tolerance band will be our settling time. So in here, as we observed, our settling times will be for between 0 to somewhere here, right? Our system reached the steady state in this between the 0.15 to 0.2, as you can see, and then it's stable, right? So the time passed until we reach the steady state will be our settling time. So as we can see from the graph, we can say it's around 6 seconds, right? But we're gonna measure it, so it's your homework for the next lab. If you couldn't do it, don't worry, we're gonna do it together next week, all right? So just everyone understand what is settling time is? Is it clear? Yes or no, guys? Yeah, understood. So is not enough. Let's take a look again then. Okay, so this background is not good. Okay, let's go one more again for the settling time. Settling time is the time required for the response to reach the steady state, right? We reach the steady state around here, all right? And stay within the specific tolerance band. So tolerance band for this lab, we say we ask for 2%, or it could be 5% or 2%, one of them. And around the final value, right? Around the final value, the tolerance with the 2% or 5%. So in here, our settling time is around 6 seconds. Right? Time passed to reach the steady state and between the tolerance band. That's the settling time, right? So let's go to our second one, which is first order electrical system. All right, let's take a look. So now we have a first order electrical system, all right? So we have your resistive load, capacitive load, input voltage, output voltage. So let's model this electrical circuit, all right? We have a X dot, right? X dot, our circuit 1 over RC FT minus X FT, your function, which is input function, which will be your input voltage, all right? As the X dot we said is the rate of the change of the output voltage. R and C are constant. Ft is the forcing function, which is your input voltage, and X is the output voltage. Right? We are not going to take this one by one. Let's go to the MATLAB again. So let me share the screen. Okay, let's clear this. So first, we're gonna take our step function. Of course, we need a function first for input voltage. All right, your input voltage. And then for the RC circuit, it will be our gain, right? In the circuit, it will be our gain. It's constant. So we have our gain for the RC circuit. We can name it the RNC, right? So we need a divide function to transfer our input function and with the converted with the feedback. Okay. And then we're gonna need our integrator for the integrated for the scope. Or integrator. All right. And then we're gonna need a scope for the output. Observe the output. All right. No, is it? Okay, so you connect your gain, your integer, connect output, and your feedback has to come from output, right? So let's start our circuit. We need a subtraction. It's deviation, so we need a subtraction. So our feedback will be negative feedback, so second one will be subtraction, and then you connect it. Connect to your RC gain, and then your negative feedback will come from your output. Let's start it. All right, should be fine. Yeah. So your step response, as you can see, step response, in 10 seconds, your value changed from 0 to 1, and here is your steady state, right? So far, so good, guys. It's clear. I just want you guys to find the settling time for the first example we did, right? And steady state for the first example. If you couldn't do it, we're gonna do it together next week. Don't worry. I just want you to do it. If you can do it, you'll get extra point about it. All right. So that's it for today, guys. See you next week.